Hello, and welcome to this online training on Intel Simics Simulator for Intel FPGAs hardware inspection tools. Feel free to pause, move forward, or go back as you need during this presentation. At the top right of the presentation, you will find a list of helpful links and resources on the subject. Let's get started. The Intel FPGA portfolio supports this transformation, including discrete and integrated FPGAs that are expected to improve processing efficiency, task specificity, and connectivity. Intel FPGAs can provide a variety of workloads in network processing as well as compute and storage acceleration. FPGAs are mass-produced, standard product ICs that can be reconfigured in the field to accelerate virtually any digital algorithm. They offer greater throughput, execution speed, and energy efficiency than CPUs on computationally intensive parts of algorithms, but with the ability to adapt quickly to changes in algorithms, data patterns, or performance needs. They can be reconfigured in the field to accelerate virtually any digital algorithm. They are available in 5 current families: Max, Cyclone, Aria, Stratix and the newest family Agilex, all with of increasing capacity, performance, and feature sets. The objectives for this e-learning are to learn the capabilities of Intel Simics Simulator for Intel FPGAs to perform hardware inspection, debugging and software testing with an Intel SoC FPGA model and functionalities through the command line interface. The agenda for this e-learning will cover topics on hardware inspection using Intel Simics Simulator command line interface, debugging and use of symbol files, as well as a demonstration for the use of hardware inspection capabilities of the simulator. Intel Simics tool is to simulate the behavior of a system. One of the main functions is to perform hardware inspection in a non-intrusive way. Some inspection features that Intel Simics Simulator offers for this purpose will allow us to understand how the simulated hardware is being integrated and then what the state of it is at a certain point of the simulation session. In the Intel Simics Simulator environment, the virtual hardware platform is presented in a tree hierarchy of namespace and objects. Each namespace can be expanded down to its sub-level objects. The first method to inspect hardware would be listing the objects using the command list-objects directly in the CLI. You can inspect the objects under system.board.fpga by entering list-object namespace equals system.board.fpga, for example. This would return a list of all objects. The output list can be long since it would display the whole list of objects you have as part of the namespace. To perform hardware inspection, there are several operation type examples that you can use. Get for performing inquiry reads. This should not have side effects on the state of the register. Set used for inquiry writes, and to change the register contents but does not trigger side effects. Read and write for doing normal memory operations that have side effects. Some target specification examples are reg. This is used for specifying the register by name. Offset to specify name of device, bank for example, or offset, and size. In an Intel Simics simulation, the CPU is the main component that drives the simulation flow by executing instructions. In some cases, the CPU instructions are translated into transactions that are sent to other components in the Intel Simics model. These transactions exercise the modeled functionality of the other components. Here are a couple of examples on the uses of commands for processor inspection using the Intel Simics Simulator command line interface. Processor status. This is a command to check the condition of the target system's CPUs. P-cell. The command is used to determine which is the current front-end processor selected and to switch to a different processor, as shown in the capture. List processors. is a command that shows the information about the state of each processor core. This is to help diagnose the current state of the system. There are multiple switches available. Use help or tab completion to see the available options. To go further with the functionalities, you can add to the name an additional command followed by a dot. Here you can take a look at the use of a couple of commands that can follow the name for the processor. To obtain more information about the processor, you can use .info and .status to know about the status for the processor in the simulation. The .disassemble and .print processor registers commands are to inspect directly on the selected CPU. Inspection of the registers and current execution mode of a processor can be done by using the .print processor registers or pregs commands. The Intel Simics model device is a representation of a piece of hardware that is modeled in software. The virtual platform can include tens of devices for which you might want to inspect them to get their status at certain points in the simulation. You can retrieve the list of the model devices that are part of the current virtual platform using the devs command. This command provides information about how many times each device has been accessed, and where they are mapped. The print device regs command allows us to get information about the registers in a device bank. The bank argument can be either a device or a bank object. In the example, you see that the UART0 bank is being explored with the devs command. If this argument is a device, the register information of all banks in the device will be listed. The register information is listed starting from the lower register offset, but the S argument can be used to list the register alphabetically. The commands have different effects on the hardware inspection. After reading the information using print device regs for UART0, the examples in the table show two columns with a set of commands that have effect or no side effects on the registers being inspected. Set and get device commands have no effect, while write and read device commands have an effect on the simulation. At the bottom you can see an example of the uses of the commands to obtain the information in the registers, and then it sets a value using the set command. A memory space is a fundamental abstraction in the Intel Simics Simulator, providing support for generic 64-bit address spaces into which memory and devices can be mapped. More concretely, a memory space takes a stream of transactions to an address space and distributes them to devices mapped into the address space in a highly efficient manner, while optionally providing address translations, byte swapping, and breakpoint support. Memory space objects can be cascaded to form arbitrarily complex mappings and support dynamic reconfiguration and remapping at runtime through attributes to support the modeling of buses with dynamic addressing. As part of the output of this command, the memory space to which each device belongs is presented in the space column in the table. A useful command is memorymap. This displays the physical memory map including translator for the current selected processor. Information from another processor can be shown using the object command parameter. Intel Simics hardware models generally output log messages for various kinds of events. The Intel Simics log system offers a very powerful system for configuring which log messages to see from which objects, at which level. That output can be configured and sent to files for later inspection. The log setup command is used to display current logging configuration or change the configuration. When calling the log setup command without any argument, this will display the overall logging system configuration. The Intel Simics Simulator can set breakpoints on code and data. Unlike most debuggers, the simulator breakpoints are not limited by what the hardware can support. For example, there is no restriction on the number of read-write breakpoints, also known as watchpoints. This makes it possible to narrow down the location of difficult bugs by rerunning the same simulation run as many times as you need. Intel Simics Simulator has a breakpoint manager that stores information about all types of breakpoints. It has commands for listing breakpoints, enabling, deleting and other common operations. The breakpoint manager is the object called BP. From there you can add as seen in the examples the different uses like list, delete, or show. Breakpoint commands for hardware inspection can be used to define if any specific object sends a message using the object argument. We can also define a specific text for which we want to break using the substr argument. The re argument can be used to break on a regular expression. We can also specify if we want to break on a specific type of message, info, error, critical, etc., using the type argument. We could have any combination of these parameters to narrow down the messages list that could cause the trigger. If no argument is given, breaking on all logs is enabled. This example of memory breakpoint shows the use of Intel Simics CLI to establish a breakpoint for memory range address being accessed. Then the command bp.list is being used to see the information about the breakpoint and its counts. Then the simulation has been started once again. The word running in the CLI prompt indicates that the simulation is running as the normal hardware would do. Then there is a second exercise of the breakpoint trigger. You can see that the hit count increased the count to 2 in the summary table. The command bp.disable is used to change the status of the breakpoint and continue with the simulation. In real hardware, the processor clock is used to synchronize the internal processes that occur in the CPU, such as the fetching of instructions, decoding and executing them. Because of this, the clock frequency is one of the parameters that defines how fast the CPU can execute certain pieces of software. In a Simics simulation, having a higher or lower CPU frequency does not affect the actual speed of simulation, but it will affect the number of instructions that need to be executed for a certain amount of simulated time to pass. If your execution only depends on executing a certain number of instructions, increasing the clock frequency will take the same amount of host time, but a shorter amount of target time. However, if there are time-based delays of some kind in the simulation, these will take longer to execute. The simulation of the execution of one single instruction is called a step. The step rate corresponds to the number of steps executed each cycle, not including stalling. Similarly, the cycles per instruction, CPI, corresponds to the number of clock cycles that are required to execute one instruction. Normally the CPI corresponds to the reciprocal of the step rate. You can also use the command step instruction and step cycle to advance the count number of instructions or cycles in the simulation. Intel Simics Tool is a full system simulator that can run target software at any different level, going from bootloaders to OS applications. When you want to debug an OS application, it is possible that there are some other pieces of software running in the background, such as other software threads, other applications or kernel tasks. To limit the scope of your debugging to just one process, or task, or kernel thread, etc., you use an appropriate debug context. Each debug context corresponds to some part of the target system. It can be a processor or the memory space of a processor, or a software abstraction like a process or thread. The ways to enable contexts are: 1. Using Enable Debugger command. This suggests based on the initial debug context if possible. 2. Using Debug Context command. This will activate the debugger and select a debug context. Intel Simics Simulator can handle temporal breakpoints. A breakpoint can be set up and this will trigger after some configurable time. Since in the simulator the concept of time can be related to CPU steps or cycles, the temporal breakpoint can also be referred to a specific step or a cycle count as measured by a given processor. The commands shown in the slide configure a breakpoint to trigger after the specified number of cycles, steps or seconds. Hardware access breakpoints can be useful to debug target software, as we can identify whenever a register or set of registers are accessed. There are several Intel Simics Simulator commands that could be used for this. The commands shown allow the setting of a breakpoint in a read or write access to a full bank of registers, or in single register defined by its name or by its offset. It also allows to set a breakpoint in accessing a set of registers defined with an address range or when the register gets written to a specific value. Many simulated machines have a text console. In embedded systems, this typically corresponds to a terminal window hooked up to a serial port on the target machine, so that you can interact with the target system typing commands to the target using the keyboard and getting replies. You can use as the argument for string any string input you decide, for example, starting kernel, to add to the console activity. Intel Simics Simulator supports a feature that allows a text console to halt the simulation on the occurrence of a given character sequence in the output. This feature is called a text output breakpoint. The Intel Simics Simulator features for this purpose go from setup of breakpoints acting over different components in the target device, to events, and to more advanced features such as debugging a piece of software using symbol files. A symbol file is used to debug a compiled image. Each processor in the simulated system has a current context, which represents the virtual address space currently visible to code running on the processor. A context object represents a virtual address space. Virtual address breakpoints are properties of contexts. Different context objects have separate sets of virtual breakpoints, and an important part of a debugger's task is to understand the system being debugged at a higher level than just machine instructions and memory contents. In the slide you can see the steps described to debug the target software with symbol files. The commands shown are to load a symbol file to a simulation, remove the mappings, and obtain information about a symbol file, among other features regarding the debugging. To learn even more about the commands and how to debug target software, go to the links and resource section provided. This example shows a code in C-debug that should be available for debugging in the target system embedded OS. The code consists of two increasing counters with initialized variables in 0, then adding them up to output the value. This simple code is being added as a symbol file with the first command. Then, it determines a breakpoint when the simulation enters a main function. You can see that the debug list is displayed. You can use the serial console in the virtual platform to display debug messages. The Intel Simics Simulator provides some commands that allow us to create log files for further analysis under the host system file system. Some of the commands that you can use for the debug log files are capture start, which is used to capture all output from the serial console to the file indicated by the filename argument starting from the moment in which this command is called. Capture stop. This command is used after calling the capture start command to stop the capture of the serial console into the file. Save to file is a command used to save the current output in the serial console, including scrollback data, to the file indicated by the filename argument. We will now move on to a demonstration of the uses of the hardware inspection commands. We will now do a couple of examples for hardware inspection using the Intel Simics CLI. The target system has been deployed and the Intel Simics Simulator has started too. The system is not currently running. Notice the prompt has the word Simics instead of running, which is an indicator if the system has stopped or is up and running like any hardware. To start, we will create a log file for capturing the information that will be generated. At this point the command log setup is used to display current logging configuration or change the configuration. The command log type is used to configure which log types to display on each object. Logging can be a useful tool for tracking error messages and information that can help inspect a system. With these commands, you can configure the log for CLI messages and enable timestamp to a log file. Now to set a breakpoint triggered by an operation on a memory address and it captured in the log file. We will use U-boot in the Serial Console window and take a look at the breakpoint. The commands bp break memory and bp.list are to set and deploy the list of breakpoints and the information regarding the triggers. Then we will start running the system and wait for the breakpoint. You will see the word Simics in the CLI prompt change to running now that the system started after using the command run. We will now wait for the system to continue and press any key to stop the booting and enter U-boot prompt. There in the U-boot prompt, a value to a memory address has been added. The bp.list displayed will change to a new count of breakpoints and the simulation will stop. Using the command bp.delete will delete the previously set breakpoint. To work with hardware inspection through the Intel Simics CLI, you can print the status for the processors using processor status. Then you can use pcell and pregs to display information on the selected processor, in this case Core 0. To inspect a device in the HPS, we will select the GPIO1 device. Use the devs command in the CLI to locate the memory mapping for this device. Linux OS in the target system assumes that 3 LEDs are connected to the pins, 2119, which are configured as output. To inspect the registers you can use print device regs. This will show a table with the information for GPIO1. These were a couple of examples to show how to use commands from the CLI to perform hardware inspection. If you want to learn more, go to the resources section in this presentation and visit the links provided to continue learning. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5 minutes quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person at an office local to you or virtually over the web. All instructor-led courses have hands-on labs exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages, called landing pages, dedicated to specific FPGA technology like and high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. This concludes the training. Thank you and have a good day.